In this last video, I just want to take a moment to summarize in question number 7 the fact that this is where we're going to see all of the different iterations of the second fundamental theorem in one practice session. So keeping in mind that the second fundamental theorem really is a chain rule process means that it's important in these problems to dictate for yourself how you're going to think about each question. Are you going to think about each question in different cases? Like letter A is going to be done differently than letter C because letter A doesn't have anything fancy attached to the x squared, but letter C does? Or is it too complicated to think about that? So you're going to do every question like letter A and letter C as a chain rule because the chain rule works 100% of the time. It ends up being almost like an unnecessary step in letter A, but you can do it as a chain rule just to remind yourself that that's technically a possibility. For people who like to do every single problem the same way and they don't like to make special exceptions, that might be a good way to go. I mean, if I was doing this problem, I would definitely think about the chain rule. Remember, you're technically taking a derivative. So first step, cancel derivatives and integrals. Second step, write out the original function, but leave a space in the dummy variable spot and plug in the new upper limit. So the new upper limit plugs in as x. And then multiply by the derivative of your upper limit. Derivative of x is just 1. This is why I said that the chain rule step isn't really necessary for this particular problem, because the derivative of x is just 1, but that is something that if you want to just think about those steps over and over again until you get comfortable with them, you could theoretically do. That's something that you can decide for yourself whether it's necessary or not. But the question that I want to make sure that I go over in this video, the question that I want to make sure that we address, because technically we've done fewer of them in this problem set, is question letter F, which, if you notice, doesn't have a traditional fundamental theorem setup. The traditional fundamental theorem problems have x at the top, this one has x at the bottom, and the fundamental theorem process, that chain rule process, only works when x is at the top. So for this particular question, what we know we need to do is rewrite it so that the x and the 6 are switched, which we are allowed to do as long as we put a negative in front of the integral. Everything about the integral itself stays exactly the same. The function stays the same, the dummy variable stays the same, at least for a second, the dt stays the same, everything stays the same. The only thing I needed to do is switch the order so that the x is on top where we expect to see it. The x that gets replaced into the dummy variable needs to always be the upper limit. And to make sure that I've compensated for that switch, I need to make a negative in the front of the integral. That's the rule of integrals that we explored. That switching the integral symbols, switching the limits is allowed as long as you have a negative in front to compensate for that switch. So I'm going to use my same rules of the fundamental theorem, and I'll do it the chain rule way just to make it consistent, even though you don't have to do it the chain rule way if you don't want to. First step, derivative and integral cancel. So again, for formality's sake, you can write a derivative if you want to, d dx, and then cancel the derivative, cancel the integral. The negative that you just wrote does not cancel, because the negative isn't part of that algebraic cancellation. The derivative and the integral are the part that are canceling, so the negative is definitely going to be part of my answer. Then, after you cancel, write out the original function. Just leave a space where the dummy variable was. So ln of 1 plus something squared. In that dummy variable spot, in that spot, I'm going to plug in the x. So x plugs in. And again, I'll just remind you with a little yellow, that's where that's coming from. X plugs in times the derivative of what I just plugged in. The derivative of that inner function is just 1. Again, if you don't want to do that times 1 because you feel like you don't need the chain rule there, that's fine. If you'd rather just be consistent, use the chain rule every time, that's fine too. You decide. Cleanup is pretty unnecessary here because multiplying by 1 doesn't do anything. So we have negative ln of 1 plus x squared, and that is our answer. So it's not that these are tedious, it's not that these are time consuming, we just have to make sure we understand why we do all the things that we do, including using that negative in the front to ensure that we have that reminder that the fundamental theorem only works when x is the upper limit, and that if x is given as the lower limit, we have to make that switch. We have to make it negative. The remaining problems in this section do contain another iteration of this negative situation and a few more chain rule examples. There are some problems for which you can use the chain if you want, but you don't have to. You'll have to make that judgment call on your own. In any case, this was a long playlist of videos to digest, so a lot of things to think about, but hopefully the concept makes sense. You're going to see these problems sprinkled in over and over again. So while I did want to take some time to really carefully explain why the fundamental theorem works the way it does, it's very rare that you'll have to spend a lot of time doing these questions. They go pretty quickly. So ironically, while page 7 and page 8 took a very long time to develop, page 9 goes by in a flash. And on page 10, which is technically tomorrow's lesson, you'll be able to do a couple more examples, but find fairly quickly that the fundamental theorem will not be the hardest part there. In the time that you have to finish up, make sure that you check the answer key. And if something still doesn't make sense, or if the theory behind the fundamental theorem still doesn't make sense, pop into office hours at your earliest convenience, and I'll be glad to help flesh it out a bit further.